Okay, in terms of goals for today, when we finish up, you should really be able to tell me what molarity is, from what it's derived, how it applies to concentration, or maybe I should say how concentration applies to it. You should be able to express the concentration of the different electrolytes that are part of a solution. You should be able to work different calculations involving molarity and dilution. So we're just going to work our way through this. When you hear the word molarity, you should be thinking quantity of solute in solution. And we've talked about solute before. We talked about solutions before, the parts of the solutions, how they interact in terms of dissociation. We've been through all of those things. So now we're going to focus in on figuring out the concentrations of solutions and working with the molarity of solutions. When we talk about molarity, we call the amount, or we call the quantity, dissolved concentration. So we're talking about concentration. Molarity is simply, we'll say, a way to measure the concentration of a solution. When I'm dealing with molarity, base level molarity, or your simplest form of molarity problems, I'm going to say that molarity is represented by a capital M, and it is equal to moles of solute per volume of the solution, or volume of solution, in liters. So it looks like this in terms of units, moles per liters. I can use this molarity, we'll say, as a conversion factor. Between the two units that I've looked at up above, between moles and liters. So it works as a conversion factor of sorts. So let's look at how it works. Let's look at a problem with it. So I've given you this problem. Calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. So once again, there's an ionic compound that I've been preaching to you about. Be sure that you know your polyatomic ions so that you can make the neutral formula. So I'm going to start out by writing down my formula, Na2SO4, which I know all of you can do at this point. And I'm going to think about what I want to do, and I'm going to break this down into steps. Eventually we can move through it in one big long chain problem like we've done before, but to start with, I'm going to break it down into steps. Then you guys, as you get into your problem solving groups, you can follow through the steps. So I'm going to start by going from grams to moles. So I'm going to take my 23.4 grams of my Na2SO4, and I'm going to begin by converting that to moles of Na2SO4. And in 1 mole of Na2SO4, of course, you can go to your periodic table and y'all can figure this out. I end up with 142.1 grams of Na2SO4. Then I can do my math. and that becomes 0.165 mole of Na2SO4. So now, that's important. Remember before we kind of boxed some of the stuff we thought we might use later. I am also given a volume in here. However, my volume is in milliliters, so I want to take care of that next. I'm going to convert volume to liters. So that'll be my step 2. So I'm going to take my 125 milliliters and do my conversion. I want to be in liters, so I'm going to put my 1 liter over 1,000 milliliters, and I'm going to do my math. And that tells me that I have 0.125 liters in terms of my volume that I'm working with. And then in step 3, I'm going to go ahead and I'm going to calculate my molarity. So I'm going to say M equals my moles over my volume of solution. So M equals, my moles were 0.165 mole Na2SO4 over 0.125 liters. When I do that math, I come up with a 1.32 molar solution of Na2SO4. So again, just a series of steps. This second example that I have is, what is the molarity of a solution made by dissolving 3.68 grams of sucrose, C12H22O11, in sufficient water to form 275 milliliters of solution? So again, we're going to write down our chemical formula, C12H22O11, because we're going to use it. I'm going to do my step 1, where I take my 3.68 grams of sucrose, and I'm going to go ahead and I'm going to convert it to moles. So in 1 mole of sucrose, I have, if you go to your periodic table and calculate this, 342 grams of C12H22O11. When I do the math on that, I come up with 0.0108 mole C12H22O11. I'm going to box that because I might use it later. I know I'm going to use it later. I'm going to take care of my volume next. I have 275 milliliters that I need to get to liters. And we know there are 1,000 milliliters in 1 liter. So I come up with 0.275 liters of solution. Step 3, I'm going to calculate my molarity, which equals moles over volume, which then will be equal to 0.0108 mole over 0.275, oh my goodness, 275 liters of solution, which gives me a molarity of 0.04 molar C12H22O11. Okay? So that's just looking at some simple molarity problems. Now, we've talked already about electrolytes, strong electrolytes, weak electrolytes, non-electrolytes. I want to take that and I want to go just a little bit further with it. And we're going to talk about expressing the concentrations of electrolytes in a given process, in a solution. And one of the processes that this really applies a lot to, and I'm sure that you've heard about it before, those of you who have taken some more advanced biology, or even perhaps human anatomy and physiology, how important this is in metabolic processes. that we examine the concentrations of the ions and the electrolytes that are present to make sure that different tissues, different processes within the human body are working the way that they should. If problems need to be fixed, it's one of the things that we often examine. If I think about this, I know that if I have an ionic compound, like we've worked with previously, and it dissolves or dissociates, we say the relative, let's say the relative concentrations of ions in solution depends on the chemical formula of the compound. So let's say, for example, I've got this NaCl on here. Let's just say I have a 2 molar solution of NaCl. When I break that apart, we know I have Na plus and I have Cl minus. We also know when I look at this that they're in a 1-to-1 ratio. That tells me if it's a 1-to-1 ratio, if I have 2 molar NaCl, then I have 2 molar Na plus, and I have 2 molar Cl minus. Pretty simple to look at. If I had 1 molar NaCl, then I would have 1 molar Na ions, and I would have 1 molar Cl ions. So I gave you an example problem. How many moles of ions are present in a solution of 1 molar sodium sulfate? So we've used that one before, Na2SO4. If I break this apart, I have 2 Na, and I have only 1 SO4. I've applied my subscript right here to my Na, because within this 1 mole of Na2SO4, I have 2 sodium. So therefore, if I have a 1 molar solution, when I look at my sodium, I've got 2 Na plus in a 1 molar solution, so I have to multiply my 1 molar, which tells me I have 2M Na plus. When I look at my sulfate, I just have my SO4 2 minus, just one of them. So when I multiply that by my 1 molar, I have 1 molar SO4 2 minus. So again, that was applying the subscript. That's where that comes from. Shouldn't be anything too confusing about that. As we move forward, we can look at a different problem. What is the molar concentration of the nitrate ion present in a 0.025 molar solution of calcium nitrate? I think what I'm going to do is I'm going to skip over that one, and I'm going to let you guys approach that and see what you can do with it as you move into your problem solving groups, and then we'll come back to it and we'll discuss it. Alright, when I'm using the molarity to calculate grams of solute, so anytime you're working with molarity, we'll say if you know 2 quantities you can find the third. So think about that for just a minute. If you know two of the quantities, you should always be able to find a way to get the third. And I've just got an example that goes along with that. How many grams of sodium sulfate are required to make a 0.350 liter solution of a, and that should say 5 molar solution? So when I look at this, I want to know about the molarity of my Na2SO4. So that's equal to moles Na2SO4 over liters of solution. So I know I've got a 0.500, got a 5 molar solution of Na2SO4, and I've got 0.350 liters of that solution. And I want to know, remember my molarity is moles per liter, but I only have 0.350 liters of it, so I want to know how many moles are actually present in there. So I can do my math and I come up with my 5 times my 0.350 gives me 1.75 mole of Na2SO4 within a 3.350 liters of a 5 molar solution. That's a way to approach that one. And then the last thing that I want to talk to you about is dilution, a process called dilution. Dilution deals with the fact that solutions can be diluted. The only way that I can dilute a solution is by adding only solvent. So I've got a solution. If I want to dilute it, I'm going to add solvent. When I do that, the concentration becomes lower, but the number of moles present remains constant. Now I want you to think about that for a minute. I'm going to add more solvent, but I'm not going to add any more of the chemical, no more moles of chemical. So the moles that I have in there remain constant. If I started with 2 moles of a certain chemical, I still have 2 moles of a certain chemical. However, I've diluted it by adding more solvent. So now I have a greater quantity in terms of liters of solution. So you have to think about it that way. When I'm dealing with this and I want to figure out one of the variables that I need, my moles of concentrated solution versus my volume of concentrated solution, I can set that equal to my dilute solution. And I can plug in what I know. So again, this is my dilute, and this would be my concentrated solution when I start. So if I use this particular equation and I move below and I say how many milliliters 3 molar sulfuric acid are needed to make 450 milliliters of a 0.10 molar sulfuric acid solution. So that's what I want to do. So I've got my mole concentrated times my volume concentrated equal to my mole dilute times my volume dilute. And let's plug in what we know. We know we have 3 molar. I don't know here what I've got. I've got to figure that out. And I can set that equal to my 0.10 molar times my quantity of solution, my liters of solution, which would be 0.40 liters. And I can simply do the math. I want to get this volume over here by itself, so I'm going to divide both sides by my 3 molar, and then I can do the math. My molarity cancels out, and when I do that math and I punch it into my calculator, I get 0.015 liters, or 15 milliliters, 3 molar H2SO4. So I just have to work through the process. What I'm going to do now is have you get in your problem solving groups, which would be our normal lab groups. I want you to go back as a group, and I want you to see what you come up with on this example problem number 4, where I've already given you some information. You've seen one example. This is just a little bit different, but I want you to go to that, and I want you to try it. And then if you're struggling or you need help, we'll come back and we'll look at it. Once you've finished that, we'll come back up front, and we've got a few more things to do.